Hello friends, today we are going to examine the physics of macroscopic systems. This is the physics used to describe systems with number of particles on the order of 10 to the power of 23, the Avogadro constant. With such numerous degrees of freedom, keeping track of the motion of each individual particle becomes untenable. We are therefore forced to combine the use of the laws of mechanics with statistics to describe the averages and aggregates of physical observables. And so, statistical mechanics was born. At the heart of this subject lies the partition function, which carries all information concerning a macroscopic system in thermal equilibrium. This is today's topic. Here's an overview of what we will talk about. First, let's look at the concepts of the macrostates and the microstates of a system. It turns out that a single macrostate can be realized by a great number of microstates. Based on these ideas, the Boltzmann distribution, which gives the probability of a system being in a particular microstate, will be derived. From this, we get a mathematical definition of entropy and temperature, which conform to our physical intuition. The partition function then arises as a key component to this distribution. To demonstrate the utility of the partition function, we go through a few applications, calculating statistical averages and fluctuations of physical observables. Most importantly, we will derive the three laws of thermodynamics. At the end, all the key ideas discussed will be summarized. Number 1. Macrostates versus microstates. Let us take the simple example of a gas consisting of point particles. Furthermore, we are only interested in the total kinetic energy of the particles. We see that the same amount of energy can be carried by many different combinations of particle velocities. Each combination of velocities represents a microstate of the system, which we denote by psi, indexed with a subscript. The macrostate makes no distinction between the different microstates with the same energy. These microstates are just different realizations of the same macrostate. In general, a macrostate is a set of variables that gives overall information about a macroscopic system. The total energy of a system is an example of a macrostate, without the details of the microscopic configurations that carry this energy. Here we introduce a standard jargon. A microcanonical ensemble is a statistical ensemble of microstates with the same energy. Its key feature is that all microstates in this ensemble occurs with the same probability. That's because one has no way of knowing which microstate the system is in, based on just knowing its energy. Therefore, they are equally likely to occur. This is known as the ergodic hypothesis. It is the result of the conservation of energy. The idea is that, given a long enough time, the system will be able to pass through all the states that have the same energy. This is the relaxation time before thermal equilibrium. Not knowing the initial conditions means, statistically, we must treat all these states on equal footing. We denote the total number of microstates with energy E as omega of E. Of course, we can never know the energy of a system to an absolute precision. There are even fundamental limits set by the Heisenberg's uncertainty principle in quantum mechanics. So it is understood that we are talking about the states that live within a finite energy interval, rather than at a precise energy. We are now ready to derive the Boltzmann distribution. So what exactly does it do? When a macroscopic system has reached thermal equilibrium with its environment, The Boltzmann distribution tells us the probability of finding the system in a given microstate. Thermal equilibrium occurs when the probability distributions describing the system becomes time-independent. After sufficient time is allowed for interactions with the environment to take place and reach some stable state. This distribution was discovered in the 19th century by Austrian physicist Ludwig Boltzmann, who was trying to establish a microscopic foundation for thermodynamics. At the time, atoms were still a hypothesis, and this was also the first time mathematical statistics was applied to classical mechanics, so the idea was both novel and groundbreaking. The Boltzmann distribution applies to the following scenario. Consider a system in microstate psi I having an energy EI and is immersed in an environment with energy much higher than the system. We assume that they form a closed system with a conserved total energy of E. And furthermore, the walls of the system also allows heat to be exchanged with the environment, but not particles. Under such conditions, the probability of finding the system in a given state psi I is proportional to the number of ways it could exist in this microstate. This is proportional to the number of microstates of the environment that is consistent with the system being in psi I. We denote this number as omega of E environment, where E environment is equal to the total energy E minus the system energy EI. According to the definition introduced earlier, omega represents the total number of microstates in the microcanonical ensemble of the system. Recall that each state in the microcanonical ensemble has the same energy. We denote a microstate of the environment as capital psi I. Let's take a closer look at omega. To express it as a function of system energy EI, we write E environment as the total energy E minus EI. Then take a log, followed by an exponential. Recall that the exponential is the inverse of the log. So this just gives the original omega function. The reason we take a log will be clear in a minute. Remember that we need omega to calculate the probability. Next, assuming that E and E environment are both very much larger than EI, which is a reasonable assumption, we Taylor expand the log of omega E minus EI with EI as the variable. We claim that the higher derivatives term of this series can be dropped. This is due to the property of derivatives of the log function. Looking at the plot of log x, we notice that the curve flattens rapidly with large x. This can be verified by taking the derivatives explicitly. Due to the large powers of x in the denominator, higher derivatives vanishes quickly with increasing x. This is exactly the situation where the total energy E is very much larger compared to EI, and so higher derivatives of log omega E with respect to E are similarly suppressed. And we are left with a truncated series where log omega E minus EI is equivalent to a linear function of EI. Substituting this back into the exponential function and absorbing the term independent of EI into the prefactor, we get the probability of the system in psi I. It is important to note that this probability is considered to be a function of EI, while the functions of the total energy E are regarded as constants to be consistent with the physical situation. Before moving further, let's introduce some important definitions. First is entropy. The entropy S is defined as Kb times the log of omega E, where Kb is the Boltzmann constant, which converts units of temperature to energy. At this stage, we can take SE as synonymous with omega E, which is the number of microstates consistent with the macrostate E. We will motivate the log in this definition later. Now we can define temperature T as 1 over T equals ds dE. Later we will show that this definition is consistent with our intuition that heat flows from higher temperature to lower temperature. Next, we introduce the standard notation beta, which is equal to 1 over kBT and is also equal to d log omega dE. We then substitute beta into the expression for the probability of state psi I. And get P psi I is proportional to e to the power of minus beta EI. We now introduce the normalizing factor 1 over z such that the sum of probabilities over all microstates equals 1. This implies that z equals to the sum of e to the power of minus beta EI, known as the Boltzmann weight of state I, over all microstates of the system. The important point is that a microstate with higher weight occurs with higher probability. Z is defined as a function of temperature through beta. Z is known as the partition function. It contains information about all the microstates available to the system at thermal equilibrium, as well as their relative probabilities. This means all the statistical information about the system is contained within it. Hence, the partition function is the most important function in statistical mechanics. The Boltzmann distribution gives us the probability of finding the system in a particular microstate during thermal equilibrium. The essence of this distribution is concisely expressed in the partition function. From this, we get the mathematical definitions of both entropy and temperature. Before we examine the physical consistency of these definitions, let's introduce another piece of jargon. The canonical ensemble of a system is the set of all possible microstates it could take when in thermal equilibrium with its environment. Energy is exchanged between system and environment, but not particles. The Boltzmann distribution gives the probability of a system being in a particular microstate of its canonical ensemble. Let's take a closer look at temperature. We have defined temperature as 1 over T equals to the derivative of entropy with respect to energy. We now show that this definition is consistent with the zeroth law of thermodynamics, which says that any two systems that are in thermal equilibrium with each other must have equal temperature. Consider the situation where two systems are brought into thermal contact with each other such that they are able to exchange energy. But taken together, they form an isolated system with a conserved total energy E. Assuming that initially, the two systems are not in thermal equilibrium, what would be the final energy of system 1 as energy is exchanged to reach this equilibrium? As for the energy of system 2, it is simply E minus E1 due to energy conservation. To answer this question, we have to look once again at the microstates that correspond to system 1 with energy E1 and system 2 with E2. The set of microstates psi with superscript 1 are all the states of system 1 which has the energy E1, and similarly for system 2, but with its own distinct set of states. We denote the number of microstates of system 1 as omega 1 of E1, and for system 2, omega 2 of E2. We again argue that the most probable macrostate of this joint system must be the one that corresponds to the most combinations of microstates. For any particular distribution of energy E into E1 and E2, the total number of combinations of microstates is just the product of the omegas of the two systems. We can just replace E2 with E minus E1, and effectively treat E1 as the macrostate of the joint system. Therefore, the most probable macrostate E1 is just the one that maximizes the omega of the joint system. There is a way to simplify this problem. We can look for a simpler function, such that whenever this function is maximized, omega will also be maximized, and vice versa. We can try our old friend, the log function. Recall that log x is a monotonically increasing function of x. This means whenever x2 is greater than x1, log x2 is greater than log x1, and vice versa. Therefore, this function fits our criteria. Maximizing this would be equivalent to maximizing omega. The function log omega has the advantage that we now have the sum of two logs corresponding to each system, rather than the product of two omegas. This is what is known as an extensive variable, where the whole is just the sum of its parts, which is a much simpler relation. Notice that if we multiply this by the Boltzmann constant, we end up with a relation about entropy. This result says that an isolated system tends to evolve towards a macrostate with the maximum entropy to reach thermal equilibrium. This is just a statement of the second law of thermodynamics. The total entropy of an isolated system tends to increase, which, as we have just shown, is simply the result of the system moving towards a more probable state. Notice that we say tends to instead of always, because this is a statistical statement. The most probable state is obviously not the only state that could turn up. Other less probable states could occur, but far less frequently, as part of the statistical fluctuation. Let's calculate the change in S1 plus 2 with respect to the change in E1 as things move towards thermal equilibrium. We can rewrite the second term as a partial derivative with respect to the argument of S2. A minus sign needs to be included, which is attached to E1. This is just the negative of the derivative of S2 with respect to E2. Substituting this back, now we use the second law at the top. This inequality can now be put into a more useful form using our definition of temperature. These two terms are just the inverse of temperature of System 1 and System 2. We can now apply this inequality to our picture. For this to be satisfied, both the temperature term and the energy term have to be of the same sign. This leaves us two cases. The first case is when they are both positive. Inverse T1 minus inverse T2 being positive implies T1 is less than T2. The change in E1 being positive means energy is flowing into System 1 from System 2. For the second case, everything is reversed. Energy flows from System 1, which is of higher temperature, to System 2, of lower temperature. Thus we see that for both cases, with our definition of temperature, we get the expected result. Heat flows from higher T to lower T. The net flow of energy stops when this becomes an equality. This is the stationary point where the entropy of the joint system reaches its maximum value, and this occurs when the temperature of both systems are equal. Thus we have shown that our definition of T is consistent with the zeroth law of thermodynamics. two systems in thermal equilibrium have equal temperatures. But at this point, we have to put up an important disclaimer. All our arguments so far only works when the systems are near thermal equilibrium. This is because we are using the above expression for entropy, which is based on omega. And as the argument goes, all microstates with the same energy in an isolated system occurs with equal probabilities, so we have been using omega as a proxy for probability. However, this is only true near thermal equilibrium when the system has sufficient time to explore all states equally. Later, we shall introduce a more general definition of entropy, which is applicable even to systems out of equilibrium. We are now ready to generalize the Boltzmann distribution. Recall that this is a distribution describing the probability for a system to be in one of a set of allowable states under thermal equilibrium. This set of states is called the canonical ensemble. While each state in it can have different energies, they are restricted to have the same number of particles. Here, we will remove this constraint and generalize this to the grand canonical ensemble. In this ensemble, particle exchanges are allowed between the system and its environment. As before, the system has energy EI with an additional variable Ni, its particle number. These are the properties of the microstate psi I that we are interested in. The same assumptions carry over from the canonical ensemble. In addition, similar conditions now hold for the particle numbers, with the total number of particles being conserved. We now introduce another standard jargon. The grand canonical ensemble is the set of all possible microstates a system could take under thermal equilibrium with its environment. Now both the energy and particles are exchanged, as in the scenario we have just described. The Boltzmann distribution then gives the probability of finding the system in a particular microstate psi I in the grand canonical ensemble. This probability is what we are going to calculate. Recall that previously, when there's no particle exchange, the probability of the system in psi I is proportional to omega E minus EI, which is the number of microstates of the environment, consistent with psi I. With particle exchange, omega now has an additional particle number dependence, n minus Ni, which is the particle number of the environment. N is the conserved total particle number. Again, we take the log of omega, followed by an exponential, in order to tailor expand the log omega with respect to the variables Ei and Ni. As before, the properties of the log function allows us to truncate this expansion, ignoring higher derivatives terms as both E and N are very large compared to Ei and Ni. While we recognize the coefficient of Ei to be beta, the inverse of temperature, the coefficient of Ni is defined as beta mu, where the new parameter mu is called the chemical potential. The minus sign ensures that particles flow from higher potential to lower potential in keeping with normal convention. We shall show this in a moment. Beta and beta mu can now be substituted into p psi I, which is again normalized by 1 over z. The sum of all probabilities being 1 implies that z is the sum of the Boltzmann weights of all the microstates in the grand canonical ensemble. This is the new partition function of a system with variable particle numbers under thermal equilibrium. Note that z is now regarded as a function of both beta and mu. Let's rewrite the chemical potential in a more convenient form using the definition for beta and entropy. Let's summarize what we have derived. For a system in thermal equilibrium, exchanging both energy and particles with its environment, we now have a new Boltzmann distribution, giving us the probability for the system to be in a particular microstate. This information is encoded concisely in a new partition function, modified by the chemical potential. We also came up with definitions of temperature and entropy, consistent with both the zeroth and the second law of thermodynamics. And on top of that, we obtain a chemical potential consistent with particle flow towards thermal equilibrium. We will prove this last statement shortly. A quick remark on how the Boltzmann distribution can be further generalized. While we have taken care of variable particle numbers, these numbers can be further divided into different species of chemical molecules, each with a different chemical potential. This allows us to examine the relative proportion of chemicals during thermal equilibrium and is an invaluable tool for physical chemists. As promised, we now present a proof that our definition of the chemical potential implies that particles flow from higher potential to lower potential towards thermal equilibrium. We go back to the setup where two systems are placed in thermal contact, exchanging energy and particles, with total energy E and particle number n being conserved. Under these constraints, the total entropy S is just a function of E1 and N1. Applying the law of increasing entropy, we have the variation of S1 plus 2 with respect to E1 and N1. The first term is what we have previously, with the variation of energy, and we get a very similar term due to the variation of particle number in the second term. We also get the same minus sign attached to N1 when we change variable to N2 in the derivative. We can drop the first term, assuming that temperatures are already equal. This means the term in the square bracket is 0. This is because the inequality at the top has to be satisfied independently for the variation of both variables. So let's just focus on the particle number variation. Now apply our definition of chemical potential. Note that T1 and T2 are equal due to our earlier assumption. We can just divide away 1 over T. Again, this inequality can only be satisfied if these two terms are both of the same sign, leading to two cases. The first case is when particles flow towards system 1, which has the lower potential. For the second case, they flow towards system 2, which now has the lower potential. Thus we now have a law that is similar to the one for heat flow. Particles flow from a system of higher chemical potential to a system of lower potential to reach thermal equilibrium. This happens until the chemical potentials are equalized. Now let's look at some applications of the partition function. We will be calculating the energy, pressure, and the particle number of a macroscopic system that is under thermal equilibrium. This is done by identifying these macroscopic quantities as averages of the corresponding microscopic quantities over the relevant statistical ensemble. The statistical fluctuations about these averages can similarly be calculated. For example, if we want to calculate x, a macroscopic variable that is expressed as an average denoted by xi and closed by an angle bracket. The average is defined by summing over I, p psi I times xi, where the psi i's are the microstates of the statistical ensemble. xi is the variable x evaluated on psi I. The probability p is given by the appropriate Boltzmann distribution. As a first example, we will derive the average particle number from the partition function. N is equal to the sum over I, p psi I, ni. Plugging in the Boltzmann distribution for p, we can see that ni can be generated by differentiating the Boltzmann factor with respect to mu, and then dividing out beta, which is brought down from the exponent, together with ni. But the derivative of the Boltzmann factor with respect to mu divided by z is just d log z d mu. Putting everything together, we have n equals 1 over beta times d log z d mu. This is our first result. We can see that the partition function acts like a generating function for the statistical quantities of a macroscopic system. Next, let's try and derive the average value of E minus mu n. This quantity is chosen simply for convenience. Knowing it together with n from the previous example, we can easily get the average energy E. As before, this is defined by taking the average of EI minus mu ni with the Boltzmann distribution. We can use the same trick again to bring down EI minus mu ni, but this time taking derivative with respect to beta instead, then correct for the minus sign. And so, we have E minus mu n equals minus d log z d beta. This is our result. Again, we see that the partition function acts like a generating function. We now calculate the pressure of the system. First note that the energies of microstates are actually dependent on the volume of the system. This is due to the fact that work is needed to change the volume of the system. If the volume is changed very slowly, the system will remain in the same microstate, but the energy of that state will soak up this work, hence the volume dependence. Work done on the system in state psi I is denoted by dwi, which is equal to dei dv times dv. For the case of compression, this is equal to minus the negative of dei dv times dv, where dv is negative. The term in the bracket is defined as pressure, which is positive, and is denoted by pi. The pressure P is then defined by pi average over the Boltzmann distribution. Note that only EI depends on volume in the Boltzmann factor, so the term minus dei dv can be brought down by differentiating the Boltzmann factor with respect to volume, then dividing out beta. This gives the result P equals 1 over beta d log z dv. Putting together all our results, we see how the partition function can be used to generate average values just by taking various derivatives of log z as a function of beta, mu, and volume. The situation is a little simpler if we don't care about the number of particles in the system. In this case, mu could be set to 0 and we'll just have the regular form of Boltzmann distribution. The average energy E will then be minus d log z d beta. Higher order averages can also be calculated. For instance, the square of energy fluctuation, delta E square, can be written as the averaging of the square of the difference between EI and E by p psi I. The term linear in EI in the bracket on the right of P can be evaluated right away by replacing EI by its average value. Therefore, delta E square is given by the difference between the averages of EI square and E square. This gives a more convenient expression for the square of energy fluctuation. Gathering all the equations needed at the top, let's evaluate the derivatives of log z with respect to beta. As shown previously, the first derivative is just the negative of the average energy. The second derivative just acts on the probability distribution P, which carries the beta dependence. dP d beta consists of two contributions. The first comes from acting on the exponential of the Boltzmann distribution, bringing down minus EI. The second comes from acting on z, which brings an extra power of z in the denominator and a minus sign, as well as the factor dz d beta. From this second term, 1 over z times dz d beta equals summing over I minus EI times the Boltzmann weight divided by z. This is just the negative of the average energy. Substitute this expression for dP d beta back into the second derivative of log z. We then have the second derivative of log z with respect to beta equals the difference between the average of energy square and the square of average energy, which is just the square of energy fluctuation. This shows that even higher order fluctuations of system variables can be generated by the higher order derivatives of log z. The partition function is indeed a powerful tool. Now let's develop the idea of entropy further. The original expression due to Boltzmann applies to a macrostate of a closed system. Therefore, all relevant microstates have the same energy and equal probability of occurrence. The number of states is given by omega. This was later generalized by the great American physicist Willard Gibbs to a form that holds for an arbitrary probability distribution. The Gibbs entropy is given by minus kb pi log pi summed over I, where pi is the probability of state I. To derive the Boltzmann entropy from this expression, apply it to a uniform probability distribution with all pi's equal to 1 over omega. This gives S equals minus kb sum over I 1 over omega times log 1 over omega. Since the summands are independent of I, the sum over I just gives an extra factor of omega. And we end up with the Boltzmann entropy. As mentioned before, the Gibbs entropy holds for more general probability distributions, not just for the Boltzmann distribution, which only applies to systems under thermal equilibrium. It is valid even when the probabilities are still changing with time and far from equilibrium. In such a situation, we cannot simply assume that the microstates with the same energy occur with the same probability, and so use their number omega as a measure of the probability of a macrostate. Using the Gibbs entropy, we now prove the three laws of thermodynamics. One thing to notice about this new entropy is that it is always positive. We claim that it is also a measure of uncertainties within a system. To see why, suppose we are 100% sure that the system is in state psi 1. This means P1 is the only probability that is non-zero and is equal to 1, which implies that the Gibbs entropy is equal to 0 due to log 1 being 0. Therefore, there is zero uncertainty about the state of the system. This is consistent with our certainty of the system being in state psi 1. Whereas if all the probabilities are equal, we are now 100% uncertain about the state of the system. The probability of each state is then equal to 1 over the total number of states, omega. Applying this to the Gibbs entropy gives S equals to kb log omega. This is the maximum value of S. Note that it is a mathematical fact that a uniform probability distribution maximizes the Gibbs entropy. This shows that S really measures the uncertainty of the system. The third law of thermodynamics states that at absolute zero, the entropy of the system will reach its minimum value. This can be seen in the following way. At t equals 0, the probability of the system being in its ground state goes to 1. This is due to the fact that the partition function is dominated by the Boltzmann weight of the ground state. All the other contributions are suppressed exponentially relative to it as t goes to 0 and beta to infinity. This certainty of the system being in the ground state implies that S equals to 0, its minimum value, thus proving the third law. We now prove the second law of thermodynamics, which is the statement that entropy will always increase with time until thermal equilibrium is reached. The Gibbs entropy depends on time through the probability distribution, so its time derivative is equal to the following, where we are just applying the product rule. The second term within the bracket becomes just the time derivative of pi once the derivative of log pi is evaluated. We find that this term is just the derivative of the sum of all probabilities, which must necessarily be 0. This leaves just the first term. The next step will be to evaluate dpi dt. dpi dt is given by the following, where the absolute square of Vij is the transition probability rate from the state psi j to psi I, while the absolute square of Vji is the rate for the reverse process. The first term on the right-hand side increases pi and is the sum of all the contributions where the initial states j make transition to state I. Each contribution is the product of the probability to be in state j, pj, multiplied by the transition rate to I, given that the system is in state j. The second term, which reduces pi, sums over all possible ways for the system to transit away from state I. Each contribution consists of the product of pi with the transition rate away from I to some state j. Furthermore, it is assumed that the microscopic processes involved are time reversible, which implies that Vij equals Vji. This means dpi dt can be written as the sum over j, the transition rate from j to I, multiplied by the difference between pj and pi. Let's substitute this expression for dpi dt back into the earlier equation for ds dt. We then obtain ds dt equals minus kb times the double sum over ij, the transition probability from j to I, times pj minus pi, multiplied by log pi. Notice that even if we interchange the indices I and j in the summand, under the double sum, the result of the sum remains the same. Therefore, we can replace the summand with one that is symmetrized between I and j. Now using the fact that the absolute square of Vij equals Vji, therefore ds dt is equal to minus kb sum over ij, half times the transition probability from j to I, times the difference between pj and pi, and multiplied by the difference between log pi and log pj. Notice that the difference between Pj and Pi and the difference between log Pi and log Pj are opposite in sign. This means the product of the two brackets is negative. Therefore, the time derivative of the Gibbs entropy is always positive. This completes the proof of the second law of thermodynamics. And we have achieved this purely by using the definition of Gibbs entropy and the assumption of microscopic time reversal symmetry. But there's a caveat to this last assumption. In elementary particle physics, there are actually processes that violate time reversal symmetry. These are called CP-violating processes and are driven by the weak interaction. We shall safely ignore these effects as they are too weak to figure in our applications. In a future video, we will present a more general proof of the second law where the assumption of time reversal symmetry is removed. Now we prove the first law of thermodynamics. It is a statement about the change of a system's energy under thermal equilibrium and is often associated with the conservation of energy. Starting again with the Gibbs entropy, we use an identity derived earlier. The change in entropy equals minus Kb sum over I dPi times log Pi. Log Pi is expanded further using the Boltzmann distribution for Pi. Thus the condition of thermal equilibrium is introduced. The expansion gives minus beta Ei plus beta mu Ni from the exponential and minus log Z from the normalization factor. This last term, with no I dependence, leads to the sum of dPi, which gives 0. We are then left with ds equals 1 over t, sum over I dPi times Ei, minus mu sum over I dPi times Ni. Here we have used the definition for beta. The first term can be rewritten as two terms, the total differential of the average energy, minus sum over I Pi dEi. The differential of Ei in the latter is equal to the partial derivative of Ei with respect to V times dV. Recall that Ei has a volume dependence. Using the earlier definition for pressure, we could write minus sum of I Pi dEi dV as pressure P. This means the first term within the bracket is equal to the change in energy plus work done by the system. We are then left with the last contribution to the change in entropy. This is sum over I dPi times Ni, which is the change in average particle number n. Note that n can only change through the probabilities, since the particle number of each microstate never changes. Putting everything together, we have ds equals 1 over t times dE plus p dV minus mu dN. Rearranging this gives us the more familiar form in terms of the change in energy. This concludes the proof of the first law of thermodynamics. All we have used are the Gibbs entropy and the Boltzmann distribution. We can see three contributions to the change in the energy of the system. The first is heat, defined by Tds, and its energy in the form of random motion. The second is just the work done on the system. And the third is due to the introduction of particles into the system. Here, we can see what the chemical potential mu really means. It is the minimum amount of energy added to the system, just by adding one particle. Now let's summarize everything we have learned today. Macrostates are a coarse-grained aggregate view of a macroscopic system. They can be realized in many ways through microstates, which carry all the microscopic details that are not of direct interest. All these microstates occur with the same probabilities for a given macrostate. The number of microstates, omega, in turn determines the probability of a system to be found in a macrostate. This reasoning is the foundation of statistical mechanics. From the concept of microstates follows the idea of entropy, an extensive variable derived from omega. This idea also allows us to derive the probability distribution of the microstates of a system under thermal equilibrium with its environment. This is the Boltzmann distribution and its concise representation in the partition function. One also gets out of this a definition of temperature consistent with the observed law of thermodynamics. Pursuing the development of entropy further leads to the Gibbs entropy, which generalizes Boltzmann's idea to a measure of uncertainty of an arbitrary probability distribution. This allows us to study even states that are out of equilibrium. For the special case of an isolated system in thermal equilibrium, this reduces back to the entropy of Boltzmann. Further applications of the Boltzmann distribution allow us to calculate ensemble averages, such as average energy and its higher fluctuations. Finally, combining the powers of both the Gibbs entropy and Boltzmann distribution, we prove the three laws of thermodynamics with only the added assumption of microscopic reversibility for the second law. Therefore, the microscopic foundation of thermodynamics is established through statistical mechanics. If you like this video, consider giving it a like and subscribe to this channel. And remember to press the notification bell so that you'll know when a new video is ready. See you next time, and thanks for watching.